Now we will move on to the scientific program. And to begin with it is my pleasure to introduce our keynote speaker, Dr. Sean Dougherty. Sean has served as director of ALMA Radio Telescope in Chile since 2017. With more than 30 years of experience in radio astronomy leadership, he has overseen major international scientific and technological projects, including contributions to JVLA in the United States of America and the SKA Observatory in South Africa. He previously directed Canada's Dominion Radio Astrophysical Observatory, DRAO, and he has held key leadership roles within ALMA organization. Mr. Dougherty holds degrees in mathematics, physics, applied geophysics, and a PhD in astrophysics. Dr. Dougherty will present ALMA in search of our cosmic origins. Please join me in welcoming Dr. Sean Dougherty.
Good morning, everyone. It's a pleasure to be here, and thanks to the local organizing committee for inviting me to give this opening talk. First talks are always a little exciting as you learn what works and what doesn't work. So if things go off the rails, just roll with it, okay? Thinking about how, I guess I'm stuck in front of this microphone, right? I can't wander around. Okay. So what we do at ALMA and what you guys do in Geodesy have got many things in common. And the most common feature is we all look out at the universe. We look out at the universe for different reasons. Astrophysics, we're interested in trying to understand. Do you have a lapel microphone? No. Okay. I'm going to wander because I much prefer wandering. Okay, that's on. Okay, so in astrophysics, we're interested in looking out at the universe to understand the objects that we see and try and understand where we come from, why the universe looks the way it does. In Geodesy, you look out at the universe at many of the same sources, and you're using those for precise position measurements here on planet Earth for a number of reasons: plate tectonics, movement of plates, timing, Earth wobble, UT1, the list goes on. But the important thing is, in common, we have the technique of radio interferometry. Today, I'm not going to try and give you a class on radio interferometry. I think most of you know that very well. But what I'm going to do over the next 30 minutes or so is to share with you some of the highlights of ALMA, why we're here in Chile, particularly why we're in the north, what a large-scale international scientific collaboration can achieve, and highlight a few of our game-changing discoveries. And then at the end, I'm going to finish on a few words of what the future brings. I'm going to talk while movies are running. So I'm basically telling you a story, and the movies will illustrate that story. So, and at the end, I'm hopeful that we have time for some questions, and I'm perfectly happy to try and answer your questions. So, what is the origin of ALMA? So, it's a very good question to ask. So, this story starts in the late 80s. When there were, in the early 90s, when there were three large projects, one from North America, one in Europe, and one from Japan. And all three of them were looking to look at the universe for slightly different reasons, but all in roughly the same wavelength frequency range, at the millimeter and submillimeter, largely to try and understand more about the cold universe, which we'd never really explored in great detail, certainly at fine detail, at high resolution, prior to the 80s. And even then, in the 80s, it was single dish submillimeter astronomy, telescopes like the JCMT in Hawaii, like the Apex telescope here in Chile, and several others in other parts of the world. Thankfully, somebody realized that if they combined these three projects together, they could achieve so much more than if they went it alone. And so that is how the ALMA partnership was formed. And you know, I stand up here and I say those words, international collaboration. As you all know, that's easy to say, it's not easy to actually do. And the remarkable thing about ALMA is it's a collaboration of 22 countries across three principal regions of the world: East Asia, North America, and Europe. In Europe, it's the 16 nations who are involved in the European Southern Observatory. In North America, it is the US and Canada. And in East Asia, it is Japan, South Korea, and Taiwan. And together, oh, fantastico, thank you. And together we form the ALMA partnership. And I have the pleasure of looking after what happens here in Chile, the principal location of the facility, but understanding that we also have support that is given to us from those three regions. And so ALMA is very much a globally distributed project. So I think I'd really want to emphasize this project really does show what is possible when, and it really is possible when a large number of countries pull together and shows what we can achieve both technically and scientifically. And I want to impress upon you over the next 30 minutes that this really is a success of humankind. It's quite extraordinary, and I think it points to what we can achieve when we all pull together. Okay, so why here in Chile, and particularly why in the Atacama? What makes the Atacama such a special place for observing the universe? And it's not just in submillimeter, millimeter wave astronomy, it is the best place in the world to do astronomy. So ALMA is located in the north of Chile. Here's a photograph taken from a Hubble space servicing mission. And you can see ALMA's the dot in the top center, in the middle of deep into the Atacama, high in the Andes at 5,000 meters. And you can see its position relative to Antofagasta. The important thing I want you to take away from this image, though, is that there are no clouds in the Atacama, or there is very few clouds in the Atacama. And that's principally due to a number of factors. Firstly, low rainfall, because what happens is that most of the rain falls on the coast, what rain that does fall, and then the air is dry when it passes through over the desert, and rises again over the Andes up to 6,000 meters. And it's bone dry. It's got very low water content. And also, because of the Andes, the Atacama is protected from the typically more moist weather that comes from Argentina and Brazil. So it's a combination of those factors that make the Atacama ideal from the sense of low water content in the atmosphere. And this photo illustrates that excellently. So what is the impact of low water content? Well, as the movie shows, the Atacama is very dry. And the thing about millimeter and submillimeter wave astronomy is that water is your enemy. What happens in the atmosphere is that water molecules absorb emission, electromagnetic radiation, between 1 millimeter and about a third of a millimeter. So somewhere between 10 gigahertz and 960 gigahertz. And the lower you are in the atmosphere, the more that absorption impacts you. And so by moving to higher altitudes, we can reduce the impact of that absorption, and hence we would ideally like to put an interferometer above the whole atmosphere. That's practically not happening. So we do the next best thing, which is to go to 5,000 meters in the Atacama. And it truly is the best place in the world to actually do astronomy. It's also a great place to build an interferometer. On the Atacama, on the Altiplano de Atacama, we have a large, relatively flat area to be able to build an interferometer where we can actually station antennas across an area. We do it across 17 kilometers, but you could actually extend beyond 17 kilometers if that's what you chose to do. So it's an ideal place from a water vapor point of view. It's also not so far from a seaport, a major seaport, Antofagasta, so you can get heavy equipment in there quite readily. So it really is a very good place to do astronomy. And we actually move our antennas around on the plateau from as close together as 150 meters to as far apart as 17 kilometers. And that gives us the ability to do astrophysics and astronomy on angular scales from about an arc minute all the way down to 10 milliarc seconds. And I know you're all familiar what milliarc seconds are, but just for those in the room that may not understand what 10 milliarc seconds means, it's the size of a 25-cent piece at a distance of 500 kilometers, just to give you an idea of of the resolution that we can achieve. Okay, so it's quite a challenge to, oops. So how did we build this thing? It's at 5,000 meters. That's physiologically a challenge. So thankfully, we were able to assemble most of it at a much lower altitude at 3,000 meters. And this movie shows the construction and really what it meant. Here you can see the parts of the observatory that were made in the 3 principal partner regions. They were all shipped to Chile and assembled on site. Now, for those that know this part of the world, it's remote, and so our staff live on site. We actually run 2 turnos, 2 shifts, each of a week long, and staff basically move to the Atacama for a week at a time, and so we provide all the facilities for them to be in the Atacama in this remote location for a week. And think of it like a village, in the sense of we have to generate our own power. We use liquid propane fueled turbines. We need to deliver about 3 megawatts of power. We run our own water system. We run our own sewer system. It really is like a little village. And it's home for roughly 250 staff in total. At any given moment, we typically have around 100, 120 staff at site, staff and contractors who enable us to run the facility. You saw in the images, there was a unique yellow truck. That is our transporter. There's 2 of them in the world. We have both of them for moving our telescopes. Each of our telescopes weighs about 100 tons. They're actually quite exceptional pieces of equipment. These antennas have a surface accuracy of about 20 nanometers or better. And so it enables us to, on the days when the water vapor content is very, very low, of order 0.1 millimeter, we can actually do observations close to 1 terahertz. So that is quite a phenomenal capability, especially here on the ground. Okay. Oh, did I go through all that already? No. Okay, so I want to illustrate some of the science now, just of what we can do. And here is, this is not an ALMA image. This is an ESO VLT image, also taken in the Atacama, of a galaxy, 2 galaxies in collision called the antennae. You can see one galactic nucleus here and another one over there. And so this picture really shows you the hot material in these galaxies, the stars, and all the interstellar gas that's been heated by the intense UV radiation from the massive stars. ALMA specializes in detecting something quite different. ALMA specializes in detecting the cold gas, the dust and the molecular gas in the galaxy. And the dust comes, as many of you may know, dust comes from the center of stars that have exploded. And likewise, the elements that make up the molecules. But it's the molecules from which future generations of stars are born. And so knowing about the distribution of dust and the molecules is very important in understanding the rate at which all the building blocks of galaxies can be assembled. And that is critical to understanding certainly how the universe has evolved the way it has, and particularly of interest right now because of the JWST, how the first galaxies formed. And so what we're seeing, we're using tools like ALMA, along with other large facilities at other wavelengths, is we're getting a more complete understanding of our origins. This particular image is important to ALMA because it was the first ever data we took with the telescope in 2011. And so this was the first formal image that ALMA ever produced. Okay, I'm going to come back to science. First of all, I'm going to just very briefly discuss the positive impacts that ALMA's had here in Chile. And I think this is true for all the other observing facilities that are here in Chile. Okay. So at ALMA, as I mentioned, we have a total of 250 staff. Where's my notes? And those staff range from engineers and managers to technicians and other highly qualified professionals who look after the telescope and help ensure that we are able to keep observing 24 hours a day, as much as we possibly can. And so an observatory like ALMA, it's very high tech. There's a lot of very specialized equipment. And so this has been a great opportunity for developing highly qualified people here in Chile. Most of our staff, 220 of them, are Chilenos. There are only roughly 30 of us from other places. And so we are contributing through developing the HQP. The other thing is in Chile, Chilean astronomers like those here at the UChile get 10% of the time. And so this has been a great boon for the Chilean astronomy community, and particularly in the development of astrophysics here in Chile. 40 years ago, the number of astrophysicists here in the country was a relatively small number. Today, it's well over 300 professional astronomers here in Chile. So the growth of astronomy with the international facilities coming here to take advantage of the amazing sky has been phenomenal. And so this ALMA and other telescopes like us have been a real vector for the transfer of knowledge and capability to Chile here. Locally, in the region of Antofagasta, we do a lot of support of local initiatives. We have a thing called the Region 2 Fund that we contribute to every year. It's essentially a grant of around $500,000 that is administered completely by the local communities. They decide what projects are supported, and that money has supported things from science education in the local school systems to solar water heating systems. And most recently, the community of Tocanao actually installed a solar power generation station for giving them power rather than using diesel generators. So our efforts in education are particularly noted. The local school in Tocanao recently was one of the top 100 schools in Chile for science, and I'm happy to say that one of its alumni has recently graduated from UChile with a degree in astrophysics. So we feel like we're making a great contribution to the local community. So to end, I want to focus a little more on the science and the new discoveries that have been made possible because of ALMA. And I want to emphasize, this is only a couple of highlights. This, we've produced to date over 5,000 publications in 13 years of operations. This past year, we had nearly 600 publications in the past year. It's really quite phenomenal, the scientific output and use of the telescope across a broad range of astrophysical topics. But I want to highlight the case of protoplanetary systems, largely because this was a real breakthrough observation that we made in 2014. And it's really about trying to understand where something like our solar system, our own solar system, where did it come from? How did it form? And what is important here is we've been asking these questions for a long time, and we didn't really have the tools to enable us to understand this this in great detail. So this is a state of sub-millimeter art in 2011. Okay, these are two protoplanetary systems, young stars, surrounded by dust. We have HL Tau on the left, and we have TW Hydra on the right. These have been studied for some time because we believe these are very closely edge-on, particularly, sorry, not edge-on, face-on, particularly TW Hydra. And this is the resolution of the telescopes. These observations were made in the Owens Valley by an interferometer in Westgard Pass at 3,000 meters, which was one of the leading facilities in the early 2000s. And, you know, those of you who are really good at understanding UV distributions and modeling those distributions, you, I'm sure, could extract a lot of information out of these two images rather than just assuming they were Gaussian distributions of intensity. The challenge when you only have a few stations, as you well know, is you're interpolating in all the gaps in the Fourier information that you have. And so you can come up with a number of solutions for fitting the UV distribution of these two images, but there's no way to pick out which one is the unique answer. And so you really need, so this was made with, I think, a 10-element interferometer. ALMA we have 66 available to us, so the number of baselines and Fourier components we are working with in any given moment is 1,200 plus. So we have a lot of information available to us at ALMA, and this is what ALMA revealed for these very same sources. Okay, this is the beauty of having 66 antennas and the ability to move them out to 16 kilometers. And you can see here's the resolution of these with these particular images. And what is very evident is that there are essentially orbital-like structures. There are gaps. There are lanes where there's a lot of dust. The dust in the center is hotter than the dust at the outside. And so this was a breakthrough discovery. And for those of you who spent any time messing around with visibilities and trying to generate images, I realize that most of your sources are compact. And so you have a UV distribution that is actually constant. The person who actually reduced these data actually thought she was looking at the beam pattern. And she struggled to remove the beam pattern, and it took some time before we had the confidence that this was correct, this was real data, the real intensity distribution, and because this is exactly what the models have predicted. And so now the whole business of looking at protoplanetary systems has become a small cottage industry. And here is just one of the early surveys of protoplanetary systems. And you can see that these structures are ubiquitous. They're everywhere. They have variations, of course. No two systems are identical. But we know so much more about what systems like our own solar system look like, and particularly how our own solar system looked 5 billion years ago. this has really been a huge boon. One area where there's been a huge boon because of ALMA. Here's just another example. And now it's really challenging our theories for planet formation. Some theories that say this is because the planets are formed in here and they basically hoover up all the dust and gas that's in these gaps through just gravitational attraction. And you can see by just the intensity distribution that there's a lot of variation in temperature across the structures like this. So another area where ALMA's made a huge change is in astrochemistry, the study of chemistry in space, particularly through spectroscopy. This is a spectrum taken at 900 to 960 gigahertz. It's quite impressive. As you can see, we're challenged by there's a large number of transitions in here, a large number of lines. And one of the issues we're seeing today is that we can certainly identify quite a number of the features in here. I think this spectrum contains signatures of glycolaldehyde and other simple sugars. But we're pushing the limits of our knowledge of lab spectroscopy and trying to identify what these lines are. And I think one of the limitations we face today, given the fact we have such good tools now, is that the analysis tools are actually not keeping up with the data collecting tools. It's a nice challenge to have, of course. So this is an area where ALMA's made a huge difference across the whole of the sub-millimeter, millimeter wavelength range. But I really can't talk about science and ALMA without talking about black holes. I'm sure many of you saw the front of your local newspaper in 2019 about the image of a shadow of a black hole. And ALMA was an important part of that experiment. Being the most sensitive sub-millimeter telescope in the world, we provided the anchor for calibration. Essentially, what we did was we phased up the 50 of our elements to basically make one big light bucket. And that provided the sensitivity to be able to detect fringes to all the other 8 stations around the world, including the South Pole Telescope you saw there, telescope in Pueblo, Mexico, in Hawaii, in Grenoble, in France, to be able to generate the resolution of micro arc seconds, a few micro arc seconds, to be able to detect the black hole. And so here's a zoom in. This is M87, which we've been studying for the past 3 decades at centimeter wavelengths, particularly with the VLBA, the EVN. But with ALMA and using sub-millimeter wavelengths, we were able to generate this now infamous iconic image of M87. And what you're seeing here is not the black hole. The black hole is somewhere in this hole. What we're seeing is the shadow formed by the black hole. And this is the material around the central black hole. The hot material that's in the accretion disk around that black hole. And now this work has been extended to our own galaxy. This M87 is a relatively nearby AGN. Sagittarius A star is the center of our own Milky Way, and this is the image that we generated. Oh, sorry, that the EHT generated. And it's interesting, if you don't have ALMA to provide that very sensitive anchor for you to be able to calibrate the baseline phase and gain, these images look somewhat different. It's a really challenging thing to do. You need good weather at all stations, and you need a large facility like ALMA to be able to provide you with that calibration certainty to be able to pull off an image like these. And now this work has advanced. We now understand the magnetic field through polarization images, and most recently, we've managed to observe, the EHT has managed to observe this object over a series of like 6 months to try and see if there are any changes. More challenging in a supermassive black hole than it is in something that's not quite as massive in our own galaxy. The things change here on a timescale of minutes, whereas over here it takes its timescales of months or more. So we're hopefully sometime in the next year or two, we're going to see a movie of how these structures change. So that's the latest, that's where this work has advanced to. Okay, just a few words about the future. It's important. The field of astrophysics keeps advancing, as many of you well know. You need to be aware that there's a 40-meter optical infrared telescope being built here in Chile on Cerro Amazonas, the ESO extremely large telescope. And that is going to provide us capabilities at optical infrared wavelengths we've never had here on the ground. If you combine the capabilities of a facility like that with the capabilities of a facility like the James Webb Space Telescope, we will be able to keep making groundbreaking discoveries about the universe. We're doing it still. Our view of the early universe has changed fundamentally in the last 5 years because of the James Webb. Undoubtedly, ELT is going to provide new insights to the universe. And it's important that a facility like ALMA, which has been now running for 13 years, is able to contribute meaningfully to these new discoveries. And so with that in mind, we are actually upgrading the telescope. What we are going to do is we're going to increase the bandwidth by up to a factor of 4. So that means that we have new receiver systems with much broader instantaneous bandwidth in our intermediate frequencies. It means we have to upgrade the digital transmission system, getting data from the telescopes to the correlator. We have to upgrade the digitizers. We have to upgrade the correlator. What's remarkable is our current correlator was one of the fastest calculating engines on the planet in 2011. It could do 10 million billion calculations every second. Today, that's not enough. To be able to process that high bandwidth, you need a machine that is much more capable. And so the new correlator is going to be about 1,000 times more capable than the current one. And we also, because we're going to be able to produce much more higher spectral resolution instantaneously across the whole bandwidth, that means a lot more data, which means a new archive, new processing, and new analysis tools. So it's a whole new world that we're going to face in the next few years. We've started this. The new correlator is recently went through an internal review to step up to its critical design review, which is hopefully going to happen sometime later this year or early next year. And so with this new upgrade, we're going to be in that same pool of great capability to advance astrophysics over the next couple of decades until somebody comes up with the next great thing that we could do, which may be increasing the number of antennas that we have to give us more collecting area and therefore more sensitivity. So with that, I want to say thank you. It's been a great pleasure for me to share some of the excitement of ALMA with you all. And I would be very happy to answer any questions you have. So thank you very much for your time.